Hello everyone, this is Dr. Bahrami and I'm here with another lecture, which is the last lecture of this semester, and we target the nonlinear programming algorithms. This is the lecture which is the continue of the previous lecture and the last week. So what we are going to see in this lecture is we are going to target constraint problems, and we are talking about two methods for them to solve them: quadratic programming and linear combinations method. So we start with the first algorithm, but before going there, let's talk about nonlinear uh, problem and particularly constraint algorithms. The general constraint nonlinear programming, as you remember, we have this general formula. So we want to maximize or minimize an objective function subjected to constraints. Here we have uh, several conditions. So the non-negativity conditions is the part of the constraint. So we do not write it separately. Then we are saying that at least one of the functions, it can be objective function or constraint, is nonlinear, and all of them, they are continuously differentiable. So since the behavior of nonlinear functions is not as usual as in linear, so I mean that it can be uh, chaos, it can be unpredicted. So because of this, you know, finding a general, a single algorithm for all model is like a very hard, or we can say we cannot have such thing. So maybe perhaps the most general result that we can apply to all of the nonlinear program is KKT conditions. We talked about it last week. So in this lecture, we are going to present a number of, actually two, of indirect algorithms. So the first algorithm is quadratic programming. So a quadratic programming is defined as the following. So we have a maximization of an objective function, and we write our objective function in terms of matrix form. So we have a Cx plus x transpose dx. So x transpose dx defines a quadratic form. So you already know it from linear algebra 2. So this part makes the program quadratic. So we are subjecting to the constraints. And what are our constraints? The first constraint is that ax less equal b, and all variables, they are non-negative. So here we have our x. What is x? X is the decision variables, coefficients. C is the coefficients. B is the right hand side of the constraint problems, and A is the coefficients of constraints, as you see, and D is a symmetric, so is assumed, symmetric, and negative definite. So D, we define it like this, so it should be symmetric and negative definite. This leads to that Z is a strictly concave. So we are saying that C, our objective function, is concave, and the constraint, which is this part, is of linear, guarantees a convex solution. So it means that we are reaching to the point, okay, which is optimal for us and gives us the best. So the formula was exactly here. So sorry, where is the formula that we had? I'm trying to find the formula. Oh yeah, it's here. So you can see that. So here you have minus 2 times D. Here you have A transpose, minus identity matrix, 0 vectors, and I. So it means that just simply you need to memorize this formula. So let's here. So I think there is a typo there, or so this is the part that you should remember. So we have 4 2 1 2 4 1, and back to previous slide. Sorry. So from here, so x2 enters, and from here you are calculating the ratio, and if you make a calculation, so you can see that the this ratio is the smallest, the minimum ratio, so S1 leaves. So as you can see, we have a value for x1 and x2, but here we do not finish because, as you remember from phase 1, r should goes to the 0. So but still it's not 0, and still we have a one positive variable here. So this lambda 1 enters, lambda 1 enters. So if you make a calculation, you can see that R1 leaves. In this case, we are reaching to the final iteration. So as you can see, we have a 0 here. So it means that we reach to the final. And the variables, we can say that x1 is 1 over 3, x2 is 5 over 6, is our optimum feasible solution. And if you enter it to the original objective function, you will reach to this number 4.16. So this method works like this. So we are changing, one quadratic problem to the system of linear equations, and then we solve it. Or this is another way. This is the another way of solving the system of linear equations. So if you do not like it, you can use with the any Gauss-Jordan elimination method, for example, and solve it, and you will reach to the same answers. So for x1 and x2. All right, there is another method, linear combination method. This deals with the problems that all constraints are linear and objective function is not quadratic. If objective function was quadratic, so for sure we use the previous method. But here, objective function is not quadratic, but our constraints are linear. We want to use the gradient method, steepest ascent method. As you may remember, we used this method last week or 2 weeks ago about when we said that, okay, we need a gradient, and then we define the step size, and then after that we had another, in order to find out the next point, we use again another type of optimization problem. So it was like a gradient, make it equal to the 0, then finding what is r there. So here the situation is the same thing. So first we are saying that we are not going to the whole period. We are talking about the neighborhood of, for example, a trial feasible point xk. So we are not targeting the uh, big period. We are targeting the neighborhood. So xk is feasible trial point, and we are using the Taylor series to vast it. So this is the formula for the Taylor series, and we are ignoring the rest of orders. So here we are vasting this multiplication, and we are reaching to this part. As you can see, xk is a feasible trial point. It means that it is given. When you put it here, it means that it is given. It is a number. So when we are saying that it is a number, it is a constant, not number. So the problem for determining the optimal reduces to the just calculating this part. So we want to maximize this part. So let's call it WK. So, uh, which is subjected to the all constraint, the original constraint. Why we need it? To be sure that it is feasible. So how it works? The given WK is constructed from the gradient at that point is an improved solution point can be secured if and only if WK at the point optimal is bigger than the uh, the xk, right? So from the Taylor series, this condition does not guarantee that it's not guaranteed that f at the optimal is bigger than f at that point, unless x optimal is in the neighborhood of xk, right? Okay, so here we want, I will jump to the formula. So we want to find the next point. So the objective is from xk goes to the xk plus 1. So we are using the formula that we already used it previously. So we are using the step size. So this means that xk is a linear combination of xk and x optimal. So this is the thing that they are the linear combination. R is the step size, and we want to have it the best value for it. So xk plus 1 is determined such that we are improving the objective function to be maximized. And because of this, xk is a function of r, so we want to maximize the following function. So because when we are putting here xk plus 1 is just only function of r. We saw it previously. So we have to make it to maximize it. So we repeat the process till the moment, till iteration that we reach to the following. So it's like a x optimal less equal than xk. So at this point, there's no further improvement, and you can say that we reached to the best value, the best solution of this. Let's have an example. We are using the previous example. This is the quadratic problem, but we can easily use the linear combination method for this type of problems as well, right? So we are picking an uh, initial trial point. This point is feasible, it satisfies the constraint. So first, we are making the gradient of the objective function with respect to x1, with respect to x2, we have this gradient. At iteration, the first iteration, we are substituting these variables here, so we reach to 1 and 3. And from here, we are creating our W1. We want to maximize, easily you can say that this is x1, and this is the coefficient for x2. So we are saying that the linear combination of x1 and x2. So x1 plus 3x2. Then what we are doing, we need to say that from here we should make a conclusion. Conclusion as from previous slide says that we are inserting w x0 in the w. So what we have here, sorry, when you put it here, what would be the value for it? So it is a half plus 1.5, which is 2. Okay, so which is 2, this one. Then for this function here, we want to maximize it. So you make a derivative equal it to 0, you calculate x1 and x2. x1 and x2. So x1 is, this is the optimal when you are making it's an extreme point of this function. So 0 and 1. So 0 and 1, you put it here, you have a 3. So by substituting x0, you got 2. By substituting the optimal of this, you got 3. They are not equal to each other. It means that we are not reaching to the optimum point. We have to continue. So it means that we need to go to the next point. So finding out the next point, we need to find out the step size. In order to get step size, as you may remember, so this is the formula that we have for x. We are creating our HR, and so it's like you substitute x1 and x2 to the original f and make a derivative equal to the 0, and you get one variable. This is just one variable, right? So making derivative equal to the 0, so you will get answer. So R1 is 1, for example, R at iteration 1. Then you substitute it to the Rx, so this is the next point, and you have the value for it, which is 4. So we need to continue. So in the iteration 2, your derivative, the same situation. I mean, since last week or 3 weeks ago, we talked about it. So you are substituting 0 and 1 into there. Here you got 2 and 2. Then from here you are defining the second function W2. So it's a 2x1 plus 2x2. You make a derivative equal to the 0. You are getting the extreme points or the maximum point for this function, which is 2 and 0. You substitute it here, so you have a 4 if you substitute 2 here. And the other one, you should substitute, it is 4. 2 times 2 is 4. And here you have a 2. So they are not equal to each other. It means that you have to go to the another point, which is x2. So x2, again, you have this. So we have a one function of R. So this is a single variable function. You are gathering R2, and R2 you substitute it again to Rx2, and F2 is a 4.16. Let's do another iteration. So substituting this one to the gradient, we got 1, 2. From here we are creating our objective function, which is x1 plus 2x2. You are making derivative equal to the 0. You are getting 2 points from it. And if you substitute both of them here, you are reaching to one answer, which is 2. So if you are putting this x1 and x2 here, you have a 2. And the x1, x2 here, you have a 2. And if you are doing the same thing, x1 and x2 substituting here, the answer is 2. It means that we are reaching to the optimum value, which is the 4 and 16, and the x1 is 1 over 3 and 5 over 6. And as you remember, this is the exact solution that we got it from the previous method, quadratic programming. So this is the last slide of this semester, and it is my pleasure to be actually, I was your supervisor, I was your instructor. It is my honor, and I wish you best of luck in your future career.